The Roads to Removal report provides a county-by-county level analysis of how forest management, cropland management, and biomass with carbon dioxide removal and storage could be utilized to annually remove as much as 800 million tons of CO2 from the atmosphere by 2050, at a cost of less than $100 per ton. But what happens if we need to remove more? That's where the final carbon removal technology investigated in Roads to Removal comes in: direct air capture with storage. Direct air capture, or DAC technologies, remove carbon dioxide directly from the atmosphere through either mechanical or passive processes. There are some key advantages of this technology, namely that we could, in theory, build as much as we need to capture emissions, and we are not constrained by the technology or by the CO2 source or where to build it, because the source of the CO2 is simply the air all around us. In addition, unlike natural solutions which require constant management, like forest management and cropland management, direct air capture with geologic carbon storage offers a fairly secure way to ensure carbon dioxide is removed permanently from the atmosphere. This is the rent versus buy concept. Carbon removal from natural solutions requires constant management, or rent, whereas carbon removal from DAC with geologic storage requires only a one-time process, or buying that permanent storage of those tons of CO2. The drawback is that DAC technologies are energy and capital intensive, with costs largely in the range of $200 to $250 per ton of CO2 removal. Dr. Simon Pang of Lawrence Livermore National Laboratory led the team that assessed direct air capture potential for Roads to Removal, and their work focused on examining costs for DAC, where such technologies could be best sited, and how much could be built without competing with other efforts to mitigate climate change, such as transitioning the grid to renewable energy.
So there are many factors to consider when thinking about where we might put direct air capture in the United States. It is really important in our analysis that we look at locations where we could pair direct air capture with wind and solar energy resources, because these are low carbon energy resources. We don't want to be emitting a lot more carbon into the atmosphere in the process of trying to actually remove it from the atmosphere. We need somewhere to put the CO2, so that means we need geologic storage formations for that. And we need a skilled labor force to be able to operate, build, and maintain these kinds of facilities. This might mean transitioning or evolving skilled labor from the oil and gas industry into an emerging carbon management industry. We estimated that we could deploy about 14 billion tons of direct air capture, and this is mostly associated in locations where we have ample opportunity for deploying additional wind and solar energy, and in locations where we also have the geologic storage reservoirs to be able to store the CO2 once we've captured it from the air.
Here's Dr. Andrew Wong, who led the Regional Opportunities chapter, speaking to where in the United States these opportunities are primarily located.
Direct air capture, really you have to highlight two key regions. The first and most obvious is West Texas. It has an amazing amount of opportunity for renewable energy generation, particularly from wind and solar, and also has excellent geologic storage capacity in the ground underneath. The second, and for similar reasons, is the Upper Rocky Mountains. There's a large amount of renewable energy resources as well as a huge carbon storage potential. Both of these regions are also really interesting because they have a large population of trained people who are skilled in carbon management.
Regions like Western Texas and the Upper Rocky Mountains have the combined potential to remove 14 billion tons of CO2 each year through direct air capture. That is a lot. You might be asking, well, should we just use direct air capture to capture all of our emissions? The answer to that is a strong no, and not just because it is much more costly to scrub CO2 out of the atmosphere than it is to avoid putting it in the atmosphere in the first place. There are other resource considerations that will also be important when assessing the potential for direct air capture.
So depending on the type of direct air capture technology, some technologies can actually consume a decent amount of water. This may be a problem in areas that are experiencing drought. By our estimates, to get us to the gigaton, direct air capture would consume, probably on the high end, less than 1% of the water that's currently consumed by irrigation, While this doesn't sound like a lot, it's certainly not a trivial number, and it may be more important to consider when looking at regions of the United States that are experiencing things like drought.
But if we are thoughtful about how we deploy CDR technologies like DAC, it can bring co-benefits and help communities with the energy transition. Here's Dr. Kimberly Mayfield, who examined how implementation of direct air capture could in some ways ease the energy transition in vulnerable communities.
When it comes to direct air capture, this technology may sound really new because it's incredibly innovative, but the truth is that the skills that are necessary to pull off a direct air capture project are the same skills that come from America's workforces as we already have them. For example, immediately transferable skills from the construction, the oil and gas extraction, the mining, the power plant operation sectors. All of these people have the skills necessary to pull off an incredible engineering feat, such as building a direct air capture facility and scaling it from the small scale to the large scale for the biggest climate impact. And so in the Roads to Removal report, we analyze job statistics across all of the counties of the United States to find where we may be able to find that expertise in places that people could really use the jobs.
As we outlined in the report, there are a lot of different options that we can use in different parts of the country, in addition to decarbonization efforts that are going to be required. Direct air capture happens to be the most expensive solution out of the carbon dioxide removal solutions that we examined, and so we're going to use as much as we need, but probably not a lot more. There are a lot of direct air capture startup companies that are emerging, and that's really exciting. What I'm worried about is, if any of them fail, is that going to be problematic for the industry? I think as scientists, we're very comfortable with some experiments succeed, some experiments fail. It's going to need an all-the-above approach, and we're going to have to be tolerant of the fact that not every company is going to be a success. Not every technology is going to be a success, but we still need to try.
To learn more about the diverse approaches available for carbon removal in the United States, or to download the report, visit roadstoremoval.org.